All right, chapter 5 is all about light, particularly the electromagnetic spectrum. If you remember, I will be gone the next two classes. I plan a trip to New York around the fact that probably was going to teach a Monday, Wednesday class, and I'll teach it Tuesday, Thursday, so kind of mess that up. So let's start off with the speed of light. Ole Romer was one of the first people to notice that the speed of light was finite. Up to that point, we kind of thought it was instantaneous, or to be honest, we never really thought about it. But he was observing Jupiter's moons and noticed that they weren't obeying Kepler's law. The timing was off. This had been over a course of years, not like over a course of days. But he discovered there was like a 17-ish minute difference over the course of a long period of time. And so he went and did a little bit of math. And so he said, okay, well, he looked at it and discovered that there was more of a delay when Jupiter was furthest away. And he knew, because we knew how to calculate distances, that the distance between the Earth and Jupiter at its closest and furthest point was around 2 AU. And so what he did was he took, 2 times an AU, and an AU, if you remember, is 1.5 times 10 to the 11th meters. And then he knew that there was a 16.7 minute delay. So 16.7 minutes. Now, if you've ever had physics, minutes aren't really a standard unit. So I know that there are 60 seconds for every minute. And that cancels out my minutes. And when you calculate that, you get around 2.99 times 10 to the 8th meters a second. This is not what he got, because that's like pretty much the speed of light. He got 2.25 times 10 to the 5th kilometers a second, which is 2.25 times 10 to the 8th meters a second. So he was off. And why was off? Because we weren't 100% on distances back then. I mean, this is like 1600s. So it wasn't 100% on distance, but getting close, 2.25 times 10 to the 8th meters a second. I mean, that's pretty close to the speed of light. If I put that in there, 2.25 divided by 2.99, or minus 2.99, divide that by 2.99, I get around significant, a lot more than I thought. Maybe around a 25% error, but that was still higher. That was still pretty good for back then. And you express this as C. So anytime that you see the letter C, it just basically means the speed of light. Your book does it in kilometers a second. I generally do meters a second. For most purposes, you can just say 3 times 10 to the 5th kilometers a second, or 3e8 meters a second. You don't have to put the 2.99 because it's 2.997, 24, blah, 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 blah. But yeah, that was kind of a new event, is to discover that light had a finite speed. And that came to be more impactful in later centuries. So then we move on to light as an electromagnetic wave. James Maxwell was a brilliant man who came up with 4 wonderful equations I'll kind of talk about here in a bit, but he attempted to describe the electric and magnetic forces in fields. What is that? Well, electric force occurs between electrons and protons inside of the atom. I'm going to do a review on this later, but electron is a negative charge and proton's a positive. So the force between that's an electric force. The magnetic force is derived from those forces moving inside of, let's say, an electric field. And what are these fields I keep talking about? Well, let's see here. Something like this. This is electric field hockey. It's one of these PHET simulations, but basically put, these are 2 positive charges, and so this kind of shows you the field. And so if I click start, you'll notice that it tends to kind of follow these field lines. That's how you can think of it. And I could even make this more interesting. Hit reset, not clear. By putting, I don't know, a negative charge particle here. So now you can see that it's emanating away and emanating towards my negative particle. And so it's going to go there, and it's going to go towards my negative, and, well, it kind of slingshots around it. And if I pull it down a bit, I might just get lucky and get it to go in the goal, which is kind of the, yep, see, I won. I won. But the point is, you could think of it as every individual charge having this field around them, and everything is manipulated around them. Obviously, stronger the closer you are, and weaker the further you are. That's why it's kind of faded out. That's what he means by magnetic and electric fields. So he described those forces by looking at the electric and magnetic fields. And what he was able to do was he actually came up with 4 equations that modeled the behavior of electric and magnetic fields, which are 4 equations we still teach in the Physics 314, the calc-based Physics 2, because they're pretty important in electricity and magnetism. So he also showed that a changing electric field causes a changing magnetic field, which can cause a changing electric field, which can cause a changing magnetic field. That's a lot. What does that really mean? Well, it's kind of at its surface what I kind of said. If you have an electric field and that electric field is changing, that can cause your magnetic field, your, let's say, corresponding magnetic field, to change as well, which then can cause your electric field to change back. Kind of put this into maybe terms that I more understand. Just to be clear, you do not need to know this equation. I am just simply pointing at this for purposes that help me talk through this. But bear with me here. The partial derivative of your magnetic field in the z direction with respect to time and your displacement is equal to negative epsilon naught mu naught electric and magnetic permeability constants, and the second partial derivative of the electric field in the y direction with respect to time, second derivative, sorry. So this is one of the equations. It's actually kind of the one step before you get to the actual equation of an electromagnetic wave. This is a bunch of letters and crap. I totally know you don't know what this means, and that's fine. That's not really my issue. I can point out a few things on this, and I think you're going to understand. Couple things here. So this B stands for magnetic fields. This right here is a D. A D, particularly, it's actually a delta. I believe it's lowercase. Don't quote me on my Greek letters. But if you remember, like delta y over delta x, that's your slope. That just means change, right? And so all this really means is a magnetic field changing equals, and then some constant, we'll come back to you in a second, mu naught, epsilon naught. And then this one is E. E stands for electric, so that's a changing electric field. So what I want to get you out of this, or what I want you to get out of this, is that if you have a magnetic field that changes, it's going to affect and change your electric field, because this is just a constant. Yeah, it doesn't matter what the numbers are or anything like that, but mathematically it works. The magnetic field changes the electric field and vice versa. It can go either way. So if, let's say, this had a value of 1, and whatever constant this was made this a value of 2, if I doubled it, then this is going to change. So no matter what you do, it's going to change it. Some interesting things to note. Another thing I kind of pointed out is you may notice that this is a Z. And if you look right here, you have kind of a, not really bad. This right here is the Z-axis. This is your Y-axis. And this is your X-axis. This is called a 3D Cartesian coordinate system. Not really important for what you do, but if you, like, say, you do CNC machining, this is actually kind of important. And what this means is, see how this is the Z-axis, and you can see that the magnetic field is kind of along this parallel axis, so to speak. Well, that's not a coincidence, or that's not a coincidence. That's because it is along the Z field. And then notice this EY. And notice that if you look at the picture really closely, that the electric field right here is going up and down. That is key and paramount, that they're 90 actually degrees from each other. They're on two separate planes. And so even if you don't understand anything about the equation, I think I can at least point out that mathematically, if you have a changing magnetic field in, let's say, the z direction, you're going to have a changing magnetic field in the y direction. And to maybe answer your next question, it could easily be magnetic field in the y changing the electric field in the z, or x's and throwing it. Basically, they always have to be 90 degrees from each other because they're not along the same plane. That kind of goes beyond the scope of the class on why that is the case. But the gist of what I want you to get out of this is that your magnetic field that changes affects your electric field and vice versa. This was huge for Maxwell. This was just absolutely huge. Now, why was this huge? Why am I talking about this? Why is this important? Because we understood what waves are. But we understood waves to say, okay, if you have a median, you have a wave. A water wave, a sound wave. You have to have a medium. If you're in space, how in the world do sun rays come from the sun and power essentially Earth? Because it doesn't have a median. That made no sense. He proved that through electric and magnetic fields, these electromagnetic waves, i.e. light, can exist and actually heat up the Earth. And so that was huge and monumental, as he proved it without a medium. I keep saying median. I don't know why. I guess I did too much statistics last night. In summary, a charged particle accelerating through a field will create an electromagnetic wave. And one important is it actually predicted the speed of those waves and what happened to this, and which happened to be the speed of light. So this little epsilon naught mu naught, it turns out that if I take 1 over the square root of epsilon naught mu naught, surprise, surprise, you get the speed of light. The epsilon naught and mu naught are just kind of constants that come about if you ever take electricity or physics too. But the reality is that 1 over the square root of that speed of light. So what you got here is a changing magnetic field equals to some constant. Yeah, there's a negative there, we'll ignore it. And changing electric field. And the constant is a constant speed of light, which happens to be 3 times 10 to the 8th meters a second. That was also ridiculously awesome and brilliant of him. And so, yeah, I get, once again, you're not going to have to replicate the math. I just kind of wanted to show you, to kind of give you a better idea of what's going on. And I think somewhat you can mathematically understand like the z's and the y's and the things like that. But this is well beyond the scope of the class. I just felt the necessary to kind of fill you in on that. So, yeah, they can carry waves to the vacuum of space, which was pretty freaking cool. I'm not going to lie. So we've talked about waves. What the hell do we even know about waves? Like, what are the diagrams? What's it look like? Things like that. And if you haven't had trig, not the end of the world, but I think maybe you went over this. And I know you went over this if you took trig, maybe algebra 2. So when you have a wave, you have a couple things you need to know. Lambda is the wavelength. This is called a lambda. And it is a Greek letter. It's like wee. Pretty much anytime you see lambda, it's going to be wavelength in pretty much all contexts. And that's the distance from crest to crest, or we can go from trough to trough. Crest being the high point, trough being the low point. This, of course, is the equilibrium line, this little dashed line, because if there wasn't a wave, it would just lay along this line. And then there's something called frequency, and that's equal to 1 over the period. Well, what's a period? Let's start with that. A period is the time it takes to come from this direction, passing through equilibrium, up around, it's in the opposite direction, so it's not a period yet, back around through the, what I'm going to call x-axis. Okay? That's a period. You could also measure a period from here to here. It's basically one point along the wave that does a whole rotation. So if we're a pendulum, you'd have to wait for it to go up one direction and back the other, because that, you can calculate the period of pendulum. And so frequency is 1 over the period. So to kind of give you an idea, if you listen to 95.1, I don't know, it's sometimes if I listen to the radio, I might listen to 95.1. That's 99.1 megahertz. Mega means million. So what that means is it's 95.1 cycles. Sorry, 95.1 times 10 to the 6 cycles. There we are. Every second. So what you're doing is you're listening to a radio station. Basically, you're taking your radio and you're setting it up so it only receives electromagnetic radiation at that frequency that makes that many cycles per second. Or if I wanted the period, I would take 1 divided by that number. And so that's kind of the bigger deal about frequency. And you could also figure out the velocity of the wave, which we won't talk about other than to point out one other thing, and that's equal to f lambda, which I always call flamda. So if you know your frequency and your wavelength, you'll have the velocity of the wave. For the speed of light, that's simply c, as you'll see later. And then if you have your wavelength of light, you know the constant 3 times 10 to the 8th, you can figure out your frequency or vice versa. One other part about the wave is the amplitude. Amplitude is a lot of times your energy of the wave, and that's the displacement from equilibrium to the top, or we could also say the bottom of the wave. In speech or in singing, amplitude is loudness. Or in light, no, let's just stick with that. For vocals, it's going to be the loudness. It's your amplitude. So instead of saying you need to speak louder, you could say you need to increase the amplitude of your voice. They will stare at you. They always do. All right, so that's kind of what you need to know about a wave. All right, so I promised this EM spectrum, and here it comes. When visible light is passed through a prism at a correct angle, and you've probably seen this, in high school and middle school science classes, a spectrum is produced. It produces a rainbow. So when you see a rainbow outside, it's because light is refracting inside of inside of a cloud and multiple water droplets to produce a spectrum. The Roy G. Biv. If you don't remember what Roy G. Biv is, it's red, orange, yellow, green, blue, indigo, violet. And so we know about that. I mean, most of us do. But why is that kind of important? Because that spectrum is what we see. And if I were to scale out the entire electromagnetic spectrum, we only see a very small portion, which is kind of interesting because we evolved to see one of the most smallest portions of the entire EM spectrum. But that's what we see. We see visible light. And so this whole spectrum is kind of what I'm going to talk about. A lot of your test questions will come from knowing how to use this spectrum. What are some things to note about this? If you notice up here, it says energy increases. So this is like a wave, right? And so when the waves are closer together, it's more energetic. So that's why it says energy increases. But notice that your wavelength, which is crest to crest or trough to trough, is shorter. So everything over here is more energy. And then it'll be more energy, less wavelength. So I'm just going to say less lambda, high frequency, so high F. Everything over here is going to be less energy. We're just going to call it an E. It's going to have longer wavelengths, so more lambda. Kind of sounds like lamb chops. And it's going to have low frequency. So that's kind of the gist of what you want to know for now, is that your wavelength increases as you go left, your energy increases, your wavelength decreases as you go left, as your energy increases, and vice versa in the opposite direction. So with each one, I'll kind of say something about it, so let's start off with like gamma rays. Gamma rays are the shortest EM waves, and since they're smallest, they also have the highest frequency and are the most dangerous. Gamma rays are given off by, say, nuclear accidents, nuclear reactions, cosmic rays from the original Big Bang, or no, not cosmic rays, but there are rays out there from, like, say supernova explosions and such. Gamma rays are extremely intense. They can penetrate under the skin, and they're bad because eventually they can kind of change and give you cancers and kind of change your molecular structure, and the fact that you have cancer now and all sorts of other things you don't want. So gamma rays we don't really see too much in our daily lives. The one below that we do, and that's X-rays, and they have a lower frequency, but they're still pretty dangerous. How do I know they're dangerous? Well, number one, We can mathematically prove it, but more importantly, every time I go to the dentist and they give me an x-ray, they always walk behind something. That's because if they have too much doses of x-rays, it can actually be harmful for their body. But why do we do it? Because small doses, it's actually not bad, and x-rays can pass through the entire body, highlighting certain portions of, let's say, your bones and such, which is why x-rays are important. So even though they're dangerous, even with respect to gamma rays, even for that, we can still use them in applications for people. So ultraviolet's next. Not nearly as energetic as your X-ray cousin, but it's still obviously harmful. I mean, we wear sunscreen. I should wear sunscreen because of UV radiation. It can penetrate your skin. It doesn't go as deep as X-rays, so you can't get yourself a UV ray scan, I guess, is what you would call it. You could get yourself you might be able to get yourself a gamma ray scan if it's modeled correctly. But you can't for UV. But it's still dangerous, and it's still pretty harmful. And ultraviolet, if you know, as I'm going down here, it's just right above the visible light. And then right below that, of course, the UVA, UVB. As you know, we can actually create subsets of this, but we're not going to do that. But visible light is next. We know about that. Roy G. Biv. Okay. With respect to Roy G. Biv, it's actually kind of backwards. So Biv, so Vib, Roy G, so G, Roy yellow, or that's hard for me to do backwards. It actually goes in this direction. Because red will have your longest wavelength and blue will have your shortest wavelength. Remember that in a little bit. And then you'll notice that these frequencies, this is 7E14 hertz and this is 4E14 hertz. So they have different energies and they have different frequencies as such. So yeah, we're going to the right. After visible light, you get IR, infrared. You're going to see IR a lot. And sometimes I'll abbreviate it as IR. It just means infrared radiation. You feel this as heat. So like night vision goggles, they actually look at infrared. There are some snakes and some birds that can actually see a little bit in the infrared, which is kind of cool. Obviously we can with the right goggles on. But infrared is heat. And so that's a different form of electromagnetic radiation. So when you see light and you kind of feel like you're in the sun, oh man, it's really hot. The visible light's not what's cooking you, it's converting into infrared heat, which you then feel. You don't actually feel the visible light at all. You just feel the infrared, which is kind of interesting. Below that, below your infrared, you got your microwaves, which kind of seem dangerous because we cook things in microwaves. It's a little bit different, but they're not that dangerous, but they have a longer wavelength than infrared. And then finally, you get to radio waves, which then have the longest wavelength and lowest frequency of all. Some of them are pretty big. Notice that it gets down to 1,000 meters. And that's a lot. That's a kilometer. That's like 0.61 miles. And that's just the wavelength. So that would mean between here and here of certain radio waves is around 0.61 miles, which is a lot. Also, it's very low frequency. Very, very low. You're still thinking, oh, that's 100 hertz, 100 cycles a second. Oh, yeah, it is, but relative to 10 to the 24th, yeah, it's pretty low key. And of course, we know radio waves because we listen to them. Radios, as we'll get into chapter 6, are really important with telescopes. Radio telescopes are huge and have huge advantages. So yeah, that's kind of what you need to know, at least I think, about the electromagnetic spectrum.